In this video, we're going to be learning about binary counters. Now on the screen, I don't have a binary counter. If you've seen the previous videos, this is where we ended up at a frequency divider. A binary counter is it actually is a frequency divider, but there is one more little thing that we have to talk about to make it count up or down or forward or reverse. Before we go over how to connect it, let's do a quick review on binary counters. So here, counting in binary, I'm going to use only 4 place values or 4 bits to keep it simple, but you could go up to as many as you need. So as you can see, we start from 0, 0, 0, and we end when it's a 1, 1, 1 or 15. So as I'm counting from 0, 1, 2, 3, 4, etc., I want you to highlight here in red that the ones bit is changing state or toggling every single time. So you can see in red. In green, you can see that the twos place toggles every other time or every 2 times or half as frequently as the ones place. The fours place toggles every 4 times or a quarter as fast as the ones place or half as fast as the twos place. And lastly, the eights place in this example toggles every 8 times or half of the blue, a quarter of the green, or an eighth of the red. As you can see, it's just toggling. Every bit is just a flip-flop that toggles, and it's dividing the frequency in half every time. I want to point out that, again, this one toggles every time, this one every 2, the 4s every 4, and the 8s every 8. Putting it together, I want to make sure you see the difference. What happens when you count forward or when you count in reverse? Forward is just my way of saying counting up, like 1, 2, 3, 4, 5, or counting in reverse is counting down, like 10, 9, 8, 7, 6, etc. So notice that on this left table, I'm counting from 0 all the way forward until 1, 1, 1, 1. On the right table, I'm counting from reverse from 1, 1, 1, 1, 15, all the way down to 0. And the pattern is the same in that they're all toggling. Every flip-flop is just toggling. It's just toggling half as fast as we go up in the place value of the bits. I want you to notice that on the left side, the 2's bit toggles. Oh, the 1's bit toggles every time. That one's the same for forward and reverse. But look at the 2's place here. On the 2's place, the 2's place changes state when the 1's place goes from a 1 to a 0. See that? The green arrow shows that the 1 is going to a 0 because that's when the 2's place is changing. Same thing for the 4's place. The 4's place changes state from 0 to a 1 when the previous bit, the 2's place, goes from a 1 to a 0. Do you see that? And the same thing with the 8's place. The 8's place changes states from 0 to 1 when the previous place goes from a 1 to a 0. So what you should know about counting forward is that it requires a flip-flop for every bit to always be just toggling. And you need to realize that it toggles on the falling edge when the previous bit turns from a 1 to a 0. On the other hand, if you look on the right-hand side, you have the same pattern in that it toggles every time, every 2, every 4, and every 8. But look at the difference. In the green arrow, it shows that the 2's place, well, again, the 1's place toggles every time from the clock source. Here, the 2's place goes from a 1 to a 0 when the 1's place goes from a 0 to a 1. So notice this is backwards. This one on the left, the forward counter, toggles when it goes from a 1 to a 0. The reverse counter toggles when it goes from a 0 to a 1. Same thing, 0 to a 1, 0 to a 1. Therefore, if you want to count in reverse, you have to transition or toggle on the rising edge. I always remember it like this. Forward toggles on the falling edge, forward falling. And reverse toggles on the rising edge, reverse rising. Forward falling, reverse rising. So that's what you have to remember to make a counter. It's just a frequency divider, but if you toggle on the rising edge, it's gonna count in reverse. And if you toggle on the falling edge, it's gonna toggle on the sorry, if you count forward, it's going to toggle on the falling edge. If you count in reverse, it's going to toggle on the rising edge. Well, what does it mean? Well, the simplest one to make is the reverse counter, because what happens is you just, whenever the Q turns on, whenever the previous bit turns on, you just go from Q. Let's look at it and then we'll come back to this slide. So this is my frequency divider from the previous slides, from the previous video. If you haven't seen it, it's there also on the same channel. So here I have a flip-flop, and I'm using a D flip-flop. You can do this with a JK or a D. It doesn't matter as long as it's always just toggling. So what I'm going to do here is I'm going to modify this to make it look kind of more sideways so that it's not kind of cascading down. So I'm going to make my page larger. So this is another little example to tell you how. In Multisim Live Online, the maximum page size is 200. So that's something to know. For now, I'm going to hide, no, it doesn't matter. I'm going to make that a little smaller. I'm going to move these two to go to the right. And actually, I'm going to move the whole thing down. Okay, so what we have, again, let's just start from the beginning. We have a clock source, we have a flip-flop. I'm ignoring the overrides for now. I'm not going to set anything. I'm just going to make it count forward or reverse. This light, just to get it out of the way, I'm going to put it up here. And then what I'm going to do is this one right here, this counter, I'm going to line it up so that it goes from right there, the light and this lamp. I'm going to put it up here so it gets out of the way, but we can still see it. Now, I'm not going to connect them to each other yet, because that's where actually I'm going to show you that it counts forward or reverse. So I have 3 place values right there. Why is it out of, oh, I moved them too high. OCD, there, okay. So then I have this right here. I'm going to move it up out of the way. And then this one, I'm going to move it up out of the way. And just to keep it the same as my PowerPoint that I just showed you, I'm going to add one more place value. So right here. Okay, so each one of this flip-flop right here, if I press play, you're going to see that only the first clock is toggling and this pinkish purple one is counting. Let's see. Okay, so as you can see here, let me scroll down. These 3 are not connected to anything. Even though they're set to toggle, there's no clock, so it's not working right now. But I do want to point out that my input clock, the frequency, I have it set to 100 Hertz, and the output frequency is half of that. So this one is going to become my first bit in my first place value, because it's the one that toggles the fastest. Okay, I'm going to slow it down just because I'm not going to be able to explain it so fast. I don't think I'm going to make it back to like 20 Hertz. Okay, so again, just to emphasize here, we just built the ones place that's toggling on and off, on and off, on and off every single time. Either reverse or forward, the ones place, you always do it like this. You just connect a flip-flop to toggle and it's going to turn on. So this one, I'm going to label it as my ones place. The one, ones place. Oh, I cannot use apostrophe. Ones place. Okay, there you go. So that's my ones place. As you can see, this one right here is going to become my twos place. So let me change that label so that we understand. So this is my twos place. And what I wanted to do is I wanted to blink half as fast as the previous one. Okay, so if I connected, notice the clock, this is where it gets tricky, but it's not that hard, especially because these flip-flops are all active high and positive edge triggered. That means that when the clock gets a 1, a rising edge, it's going to trigger. So again, going back to here, let's count, but if we count on the right, if we trigger on the rising edge, if we connect to Q, it's going to count in reverse. If we trigger on the falling edge, when Q turns off, then it's going to count forward. Well, when Q turns off, the inverse of Q turns on, and that's what it gives us our trigger. So if we want to count forward, we connect to the inverse of Q. That's going to give us our falling edge, forward falling. If we connect it to positive Q, it's going to count in reverse. So we want to count in reverse, we connect it to Q. We want to count forward, we connect it to not Q. Okay, so let's see both so you see the difference. So I'm going to connect it to count forward on the falling edge to when Q turns off, so not Q. So I always think about like falling lower, it's gonna count forward. So you connect it to the inverse of Q. So let's press play and see that this is counting properly. This is the ones place, and then this is the twos place. And so we can see it's counting. There we go. So it's gonna be 0, 1, 2, 2 and 1 is 3, 0, 1, 2, 3, 0, 1, 2, 3, 0. You see it? So it is counting in binary. Now let me show you what the only change you would need to make is delete that wire and connect it to the rising edge if you want to count in reverse. So all I did was connected the clock to the previous Q instead of the inverted Q. And now when I press play, it's going to count in reverse. So it's going to be 3, 2, 1, 0, 3, 2, 1, 0, 3. Get it? So that's the only difference. And it's just a ripple effect. That's why these are also called ripple counters. If again, I have my flip-flop set to always toggle. If it was a JK flip-flop, which I can show you also, it's just a matter of connecting flip-flop, JK flip-flop. The only difference would be that you connect. We're not changing the limits of this counter at the moment. We're just making count forward or reverse. So I'm going to ignore these. The only difference is that you would connect it to power. In Multisim Live, there's no VCC, so I would have to use a digital constant. So I would connect both a J and K to power. You get rid of the wires so that it's not as messy. So this one would just be my power, or 5 volts. And even though it's a switch, because that's what's available in Tinkercad, in Multisim Live, I probably wouldn't connect it to a switch. I would just connect it directly to 5 volts or VCC. And then I would just connect. So this is the exact same thing. You would connect this to the clock and the output Q to the light. So this is the only difference, how you connect it to toggle. So that's why I'm not so worried about showing you JK or D. It's the same thing. I'll show you a picture of the final one anyway. So I've connected 2 bits again. Now let's add one more. Here, if I connected the same. I can't do this because that would be wrong. As you can see up here, I have it to Q. So this one must also be to Q. If I connect Q and then not Q on this one, it doesn't count in binary anymore. It generates some sort of different pattern. So I'm going to connect this one up like that to the Q and this one up to the Q. And so now, as you can see, I'm going to have all 4 places. Let me change this name so that we are all, make sure we go. This is the 4th place. And this next one would be the 8th place. And I could keep going, 16th place, et cetera, et cetera. So what I'm going to do now is press play, and you're going to see that, and you can see on the chart also, I'll point out the difference between counting forward and reverse. But let's see, I'm counting in reverse, so it's a little bit, let's get to a place where I can follow. So that's 8, 7, 6, 5, 4, 3, 2, 1, 0, 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. As you can see here down at on the right hand side on the grapher that shows the state of all the output cues. The green is the clock. That one is not part of our counting bits. That one is just set as the source that creates the pattern. Our bits are, the pink is the ones place, blue, as you can see, is the 2s, orange is the 4s, and dark blue is the 8s. Notice the frequency just gets divided every time, right? And I want to point out the following. It gets triggered on the rising edge. So let me stop the simulation so that I can then zoom in a little bit here. If it lets me zoom, oh, it's a little laggy. There it is. Okay, so what I want to do is point out, I'm going to zoom in a little bit so that you see that all these changes are happening on the rising edge. So I'm going to put my mouse down here and use my scroll wheel to stretch things. So as you can see here, look, the ones place goes on the rising edge, and that causes the twos place to toggle. It was 0 and it became 1. On the rising edge of this one, then this one toggles. It was 0 and became 1. It happens to be in that case, but it doesn't always have to be. When this one had a rising edge, this one toggled. This one was a 1 and it became a 0. So let me find a different place. This one, yeah, here we go. So it just depends on what number you're counting on. But notice the point that I'm trying to make here is that when you're counting in reverse, the changes happen on the rising edge of the previous place value. As opposed to if I were now to change this to a forward counter, the only change I make is connecting the clock to the falling edge, or when Q turns off, the inverse of Q will be the one providing the trigger, because that will turn on when Q turns off. So now connected to the falling edge, this thing's going to count forward. This counter is going to count forward. 0, 1, 2. It's a little slower. Now I want to notice it only the things toggle when the green wire, not the green wire, the previous bit. So in this case, the pink wire turns off a falling edge. That's when things change. Look, not there, but here, falling edge, things happen, right? Falling edge, things happen. And it's a ripple effect. The pink makes the blue toggle, makes the blue makes the yellow toggle, and the yellow makes the blue toggle. So they're both counting in binary. As you can see here, this is all zeros. You can actually, if I stop the simulation, you can see it really clearly that it's counting in binary. At this point in time, these are all zeros. If I read, this is the ones place, so that's the 8s, that's 0, 0. Excuse me, 0, 0, 1, 1, and then it's 0, 1, 0, 0, 0. So you can just count over and over and over, and then you see that it is counting in binary. It's following the pattern. And let's see. Yeah, so there you have it. Let me just double check, because I think I had a brain fart and I couldn't follow along for a second. So here we have 0, 0, 0. They're all off. Ignore the green one. Let me move that out of the way, because that one's not part of my counting sequence. It's only the pink, blue, and yellows. So that's 3, 0, 0, 1, 1, 0, 1, 0, 0, that's 4, 0, 1, 0, 1, that's 5, 6 would be 0, 1, 1, 0, 0, 1, 1, 1, that's 7, and then it's 8. All of them are off except the 8's place, and then it becomes a 9, and then a 10. You got it? So there you go. This is binary counters. It's just a frequency divider that has, it's just a frequency divider that has the triggers set to the falling edge for forward, or the trigger set for the rising edge for reverse. And I do have a picture of all the counters connected together. Let me take a second to show you those. So here I have a picture of all the 4 counters counting forwards and reverse. That's what they would look like. On the left, you see JK flip-flop counting, and on the right, you see D flip-flop counting. They notice the difference. They have, the JK has all the JKs to power, and the D has that loop around to make it toggle from not Q to D. Aside from that, on the top, we have the forward counters, or counting up, and the clock is connected to the falling edge. And on the bottom, we have the counters counting in reverse, connecting to the rising edge, the clocks. The first flip-flop always connects to the clock, so that's never different. One more thing I want to point out, as you notice, the ones place is always this first flip-flop. The one that blinks the fastest is the ones place, as you saw on this one. The ones place is the one that blinks the fastest. When we write our numbers in binary, the ones place, the least significant bit is on the right-hand side. But on our flip-flops, we have it on the left. So either if you label it, it's really obvious, as I have here, 1s, 2s, 4s, and you know. But if you're not labeling, or if the labels are out of order, like are not shown like this one, as long as you put them in the right order, then it's fine. So notice what I did, the ones place, I moved it to the correct location. So if you read these in order, they are correct. If they're not in order, like on the left, then make sure you label them so that you know which bit is which. Right, so those are binary counters, J, K, and D. You can make counters with other flip-flops, but these are the ones that I wanted to show you today. All right, thank you.